So last time we graphed sine and cosine functions on a Cartesian plane or a trig plane so that we wouldn't have to deal with the wrap around and around and around that happens on the unit circle, so that we could distinguish the difference clearly between the angle 0, for example, and 2 pi, because they are different angles in nature, but they're not different angles in position. So we looked at the fact that we were lucky enough to be able to use exactly the same graphing tools that we used for polynomial functions, exactly the same tools to graph trig functions. The only difference is the shape of the graph would be determined by which trig function you were dealing with rather than with which f of x. Real quick, let me write out the polynomial version just so that we can see. So the general form is some function, it could be one of a number of functions, some function of x where there's a shift or a translation on the x-axis and a shift or a translation on the y-axis, and some squeeze or stretch function or some squeeze or stretch action on the graph. With a trigonometric function, instead of having different functions, we have different trig functions. And so the general form I write is a trig, the quantity x minus h, and then plus k. So we're going to look at one last thing and do a couple of definition changes for today's lesson. So if I look at this, this form, which is identical to what we know from polynomial functions, I want to squeeze a value right inside of here. And this value is it's not the letter P, it's the letter B, but B represents the period of the function. Okay, and so what that means, and I'm going to use just sine, and I might do a correlation with cosine, but we're going to start off with just sine. If I take the sine function right off of the unit circle and I make no adjustments to it, this is what it looks like. We know that it starts at 0, 0, ends at 2 pi 0, and it crosses the y-axis at pi 0. Well, the standard period for this function is 2 pi, just meaning that the function starts and completes one full cycle in 2 pi units. Now, we know that sine functions go on and on and on, and that they presumably came from somewhere else in exactly the same pattern, but we want to know what is the period of one complete cycle. And for us, knowing that doesn't necessarily mean the cycle has to be evaluated from 0 to wherever it completes. It's anywhere on the cycle. If I were to look at it first from here, oh, that's a bad example for the extension I put on. Let's say if I started here and followed the function until it completed a cycle and just began to repeat again, I would end up here, and I'd be able to say, with just a slight shift, I'm still looking at p equals 2 pi. So the period of a sine or a cosine is 2 pi units. Some of the other trig functions have different periods, and we should say that all trig functions, and we'll look later at some of the others that have a different period, all trig functions are called periodic. I trust that I don't, I trust that I don't need to explain the word periodic because we're talking about the period of repeat for a trig function. But I would like to point out that for sine and cosine functions, we have the additional phrase sinusoidal. Or we say that they are sinusoids. So sine coming from sine, meaning they just curve up and down and up and down and up and down. They never break. They always repeat without any sort of a break. And you'll find that all the other trig functions have a break in them. So they're periodic. They repeat over and over and over in exactly the same way, but they're not sinusoidal. Only sine and cosine have the sinusoidal pattern. Okay, so when we look at B and we're talking about period, we want to include another way of looking at period, which is called frequency. And we'll look at that in just a second. So B also means frequency. They're sort of inverse. They are actually mathematically inverses of each other. But in the real world, you can think of them as an inverse way of looking at the exact same phenomena. If you look from one direction, you could discuss the period. But if you look from another direction, you could discuss the frequency. And so let's look at that real quick. So I'm going to start over here, and I'm going to give us another sine function, or sine curve, in one period. So this is 2 pi units. So I can say, as I did before, that the period of this sine function is 2 pi units, which is the standard position of a sine curve. I haven't done any squeezing or stretching or moving about. So what if I were to instead, I always have to sketch in my targets. You can see that this is a total sine function, right? It's a sine curve. It starts at 0, 0, but this one ends at pi. So the period of this green function actually equals pi units. So it starts, runs through one full cycle, and ends before or at reaching pi on the x-axis. So what is that about? How can we describe that? How can we put that into what we know about graphing functions and using our general form of an equation? One other example is let's see, I have to stretch out my graph a little bit. I'm going to double it and end up at 4 pi. End up at 4 pi. So if I were to take another version of a sine function, I'm not changing the elevation, notice they are all just as high and just as low. The amplitude is still the same. But this purple function, or this purple version of a sine function, is a period, or has a period, of 4 pi units. From start to the completion of one cycle takes 4 pi units. So that's the period. The other way that I could look at this is I could say, let's look at this middle one. How many complete cycles? How many cycles can I complete in the standard 2 pi units? Well, the second one, I can take one cycle finishes in pi. So the second cycle would have to finish by 2 pi, which means I can get 2 full cycles in the standard 2 pi units. So the frequency is 2, because 2 full cycles can complete in 2 pi units. For the purple graph, the frequency actually is 1/2, because I'm only able to complete 1/2 of the cycle in the standard 2 pi units. And for our standard graph, the frequency, clearly, I complete 1 full cycle, so the frequency would be 1. So these are nice, pretty integer values, or fractions, actually. So nice, pretty values, though, that we can work with. It's not always true that we finish 2 complete cycles in 2 pi units. We might finish 1.2639 of a cycle in 2 pi units. So we have a formula to work back and forth between period and frequency. And we're going to use the number b, or the variable, whatever number is out here in front of our x action. So whatever b is used to determine the period and the frequency. So our two formulas are, and let's start with period, which is simply to divide 2 pi, the standard period, by whatever the actual period of this function is. And we want to keep b absolute value. It's possible for b to be negative, but we only care about, because we're talking about distance, we only care about the distance of b. We're not talking about the sign or nature of b. So let's look at our middle function real quick and just kind of sketch it in. If I were calculating the period for this green graph, I would say the period is 2 pi, and I'm telling you, you wouldn't necessarily already know this, but you can assume that the period of this function in its equation would have to be 2, because 2 divides by 2, leaving 1, and I'm left with pi. And so if the period is pi, then b has to be 2 for that graph. All right, let's look at the other one then. And it says that frequency is the inverse of period. So frequency, just the inverse of period, would be absolute b over 2 pi. So if I were calculating this purple graph, I would be given a b value that lets whatever I divide b by 2 pi would give me a frequency of 1/2. And so that would have to be a b value of 1, or a b value, excuse me, of pi. So canceling pi would give me a frequency of 1/2. So in this case, I just created b values, what seemed like out of whole cloth, and it just to make the example that b is used in this manner. But the truth is, you're actually given b as though it's invented out of whole cloth. So I haven't done anything really unacceptable for the example of using an equation to graph trig functions. So I have a couple of name or vocabulary words to cover, and then I think I'll do my examples on separate videos. I'll do one with a sine and one with a cosine function, and you can use your time however you think is appropriate. So A, and I think I covered this in the last lesson, A, which is a squeeze or stretch in a polynomial function, we use for amplitude, and we use the word amplitude. And remember, it tells you that a graph may be higher or a graph may be lower. So it heightens or it shortens the distance from the line of symmetry through the center of the graph. Amplitude tells you higher or lower. B is the period, so you don't need that. And then H, in this case now, H is the phase shift. It does the same thing. It tells the graph to move back and forth along the horizontal axis, but we call it phase shift when we're talking about trig functions.